Please teach me how to use the force method.
And I shall. Alright, so hopefully you're ready to learn the force method for indeterminate structures. So again, I want to take a look at this one-dimensional bar subjected to an axial load. So this is the example that we've been using throughout this set of notes. So you see, we have a load acting here at point C, and therefore we would have reactions at both A and B. And I drew my reactions to the left because both of them would be opposing the applied load P. With two unknown forces and only one equation from equilibrium, this makes the problem a statically indeterminate system. We can use the engineering toolbox to solve the problem, but we want to explore the force method. In the force method, we will use a superposition of the problem. Superposition, if you recall from statics, is just the separation of a problem into smaller solvable problems that add to the result of the initial problem. Okay, so we're basically taking a complex problem and breaking it down into smaller problems that we can solve, that we know how to solve. We know how to solve these smaller problems, and if we choose these smaller problems correctly, when we add the results from the smaller problems back to the original problem, we should get back to the original problem. Let's see how to do superposition for this example. So in my original example, I have a load of P at point C, and it is fixed at both points A and points B. So I develop some reaction AX and BX. All right, when breaking this problem into smaller parts, I'm first going to remove that reaction at B. So I want to eliminate the wall at point B. What would happen if I just eliminated the wall at point B? Well, if I eliminate the wall at point B, I would imagine that this bar would extend a distance to the right. So because of my applied load P, the bar would stretch. And I would experience some deflection, which I'll indicate as delta P. This is a deflection of the bar to the right due to the applied load P. However, I can't just delete the wall. The wall actually has a reaction. So in my second free body diagram, part of my superposition, I will apply the reaction Bx at point B. What will this do to the bar? This will cause my bar to shorten. So it'll push the bar a distance that I refer to as delta Bx. So as you can see, I define two deflections at the end of the bar at point B. If I return back to my original problem, the problem indicated on the left-hand side of the page, I can then look at what my deflection at B has to be. In this case, because B is a rigid wall, delta B would equal 0. I then set up what we call a compatibility equation. In this compatibility equation, I say that my deflection, my total deflection at point B, has to equal the cumulative deflection of delta P plus delta Bx. I hope this method of superposition makes sense to you. We can even extend superposition to the forces. So you can see throughout these free body diagrams, I drew my reaction at A. So my total reaction AX will be equal to the reaction from case 1, where I removed the support at B and applied the load P, so AX1, plus my reaction due to the force Bx applied in case 2. All right, so I see that I just add those two together and I would get my reaction for my actual problem. All right, we will deal more with superposition in our next lesson. So if you're not totally getting this, it's okay. But that is the essence of the force method, breaking down a complex problem into two smaller, more easily solved problems. All right, look forward to seeing you next time. Now we know how to use the force method. We'll take a look at an example in the next lesson. For now, go ahead and
go out into the world and start taking down all those statically indeterminate problems around you.